I have avoided this channel. The amount of times that I have to correct people about quantum gravity, time dilation, the double slit experiment that they always get wrong because an electron is a particle with a field flowing through it and not photons. Let's just watch this.
Thank you to Brilliant for supporting PBS. If we discover how to connect quantum mechanics with general relativity, we'd pretty much win physics. There are multiple theories that claim to do this, but it's notoriously difficult to test them. They seem to require absurd experiments like particle colliders the size of galaxies. Or we could try to physics smarter instead of physicsing harder. Let's talk about some of the ideas for quantum gravity experiments that can be done on a non-galaxy-sized lab bench, and in some cases already have been done.
Where's the button? No, I don't want to go there.
It's been almost exactly 100 years since quantum mechanics was discovered, and 110 since general relativity. Together, these theories explain almost everything. Quantum gives us the behavior of the subatomic world, and so the building blocks of all matter and their interactions via the quantum forces, and GR gives us the background in which that matter lives, space and time, along with the force of gravity. Despite their incredible successes in the
gravity, if I remember correctly, when I made a previous video, gravity is just momentum. And everything else carried along with it as literally everything, like I said in my comment, is affected by the like galaxies, and even our own solar system has a mutual tug Lagrange point. I may have spelt it wrong. I don't care. Lagrange, you get it. All mass pulls on everything to orbit this area. Even the Kuiper belt is pulling on the sun to move it into this Lagrange point. Not just Jupiter, literally everything in this solar system is all having an effect on where everything is moving as we move through our galaxy. In a general direction, every single physical object in the vicinity is controlling what we do in our solar system relative to that point in the middle of everything. Slightly near the sun, but not at the sun. This proves that everything is connected. And you have to realize, if it's all connected because of tugs that all add up to equal an effect that we're basically orbiting an empty point, makes you wonder, aren't black holes just space being pulled really thin? Whatever.
Domains, the two theories seem to contradict each other in deep ways. Now, there must be some master theory that encapsulates both and resolves these contradictions. But in the century following the discovery of general relativity and quantum mechanics, our efforts to find that theory have come up short.
Hold on.
The common approach to reconciling general relativity with quantum mechanics has been to quantize gravity, to make the gravitational field and so the geometry of space-time obey the strange rules of quantum mechanics. And why not? It's worked for everything else. For example, we made the electromagnetic field quantum, showing that it was mediated by force carrying photons. And that...
You realize that particles go in and out of existence all the time. These Not phantom particles, what's the word? Virtual particles, they call them, are the interactions and intersecting points of other fields, just energy areas that have tinier components in them than actual matter. And those components are kind of like ripples or whatever, but they exist, they move, and as they intersect, that's where we end up with a virtual particle, because it makes a big bump. And then they disappear just as quickly because those two intersection points now have nothing else in that area. They've moved on. Never mind.
Was a stunning success,
No.
but quantizing gravity to make the gravitational field and so the geometry of space-time obey the strange rules of quantum mechanics. And why not? It's worked for everything else. For example, we made the electromagnetic field quantum, showing that it was mediated by force-carrying photons. And that was a stunning success. But
I thought we noticed about the Higgs field, not photons. Why are you backpedaling?
gravity proved extraordinarily difficult.
Oh,
The hypothetical
holy shit.
force carrier for gravity, the graviton, has an energy so tiny that it's hard to even conceive of an experiment that would detect it directly. And then there's the
You realize electromagnetic fields are everywhere. They flow through everything. Physical, like regular matter, even plastic or your organic matter, like an apple and a mouse, can exhibit magnetic fields. And electromagnetic is the whole thing of everything. Not just the magnetic part, but the electro part. Like literally everything that is having a bit of energy around it. The electrons that are around all the things that we are made out of give us a tiny, very insignificant amount of aura. That energy, and like the reason why we can make like static electricity, almost. You wonder about quantum gravity. Try doing it just look at static electricity. That's about as close to quantum gravity as you'll ever want to get. But there's other things like an example.
fact that the field of gravity is the fabric of space-time itself. We quantize the other forces of nature with respect to a continuous background of space and time. But so far it's been exceptionally challenging to quantize that background itself. The most prominent
The microwave background, for example, as they always say, the evidence of the Big Bang or whatever, like cosmic microwave background, is a whole other thing. Although it is also everywhere, it's a separate thing, apparently.
approaches like string theory and loop quantum gravity may have made progress, but they struggle to make testable predictions. So what if we've been looking at it the wrong way around? What if instead of quantizing gravity, we should be trying to gravitize the quantum? That is, instead of trying to give quantum properties to gravity, we should accept that gravity is fundamentally gravitize the quantum. That is, instead of trying to give quantum properties to gravity, we should accept that gravity is fundamentally classical and try to understand how truly quantum matter can result in truly classical gravity. Now, we talked about approaches in which gravity stays classical in the last episode, when we explored the new post-quantum gravity hypothesis of Jonathan Oppenheim, in which random fluctuations in the gravitational field act on the quantum wave function, causing it to collapse. We also talked about the Diossi-Penrose model a while ago, in which a superposition of different spatial distributions of mass and energy is ultimately forced to choose one such distribution consistent with a singular gravitational field. There are compelling reasons on both sides of the discussion.
If you want to consider how the big ignition happened, not Big Bang, the big ignition, which is the other theory that people have like totally abandoned now. They've abandoned the Big Bang, except for they renamed it. It's still the Big Bang as far as everyone's concerned. It's just that it happened everywhere. This is what we are noticing. So the thing about gravity and the stuff that is on a level below matter. I had to get that out of my system.
But which is it? Is gravity quantized or is the quantum gravitized? Unlike many questions about quantum gravity, this one may be possible to answer with actual doable experiments.
Okay.
Let's consider the two scenarios.
How about the experiment where we had 14 kilogram objects versus ping pong balls, and we forced the ping pong balls to move relative to those weights? Now, was that static electricity that was moving them, or was it actual gravity of the big thing attracting the small thing? And it could have been both.
And see which predictions they make that we might be able to test.
Why am I pissed?
1. Gravity is quantum. This means gravity, and by extension the fabric of space-time, exhibit the various weird properties of the quantum world like superposition and entanglement. If we can experimentally demonstrate one of these things, then we know gravity is quantum. 2. The quantum is gravitized. This can be tested in the context of specific scenarios like the DOC-Penrose model or Oppenheimer's post-quantum gravity. Now, I'm going to talk about gravitizing the quantum first, but then I'll come back to tests of actual quantum gravity. In both the DOC...
You want to explain something quantum with me? My refrigerator is at a set temperature. One day it is the ice cream is melty, even though it's not that hot at all, and the other moment it's solid.
Penrose and Oppenheimer approaches, the gravitational field is responsible for...
I thought that the refrigerator and the freezer would have a more regulatory system, so it would just stay at a steady rate. Why would it fluctuate like this between solid and liquidy ice cream? I want to know that my fridge is working correctly. It's not.
Collapsing the quantum wave function. In these ideas, there's only one gravitational field, only one space-time, and quantum systems do quantum stuff within that classical background. One of the things quantum systems can do is to be in superpositions of states. They can exist simultaneously in multiple states at once, like Schrodinger's alive and dead cat. The job of the quantum wave function is to describe this range of possible states. Measurement or observation collapses the wave function. It forces the system to choose one state from the possibilities.
Okay, look, when you're talking about, I hear so many people have talked about electrons and how when you look at them with a regular system of looking, you end up seeing this blur circle. And it fluctuates with all these different patterns that are fascinating. But then when you actually look at an electron, it's a tiny little dot that fits within that blur circle, as if you took a single frame of instance. And the thing about that is very simple, that if you had cars going at the same speed, 2,200 meters per second, where's the kilometer? I don't know. It's a very fast speed. It's incredibly fast. As I said to the Science Asylum, fast, because that's what he says. And he failed, and I had to correct him. Electrons are moving extremely fast on a very tiny area of space. So that's why they seem to be everywhere, very fast, But if you were to, for example, slow down the footage, you'd be able to see the electron doing its normal orbity thing. It wouldn't be a cloud of weird probability. It would be predictable. But it's because it's happening at thousands of times per second that it's hard to notice what's going on.
If gravity is classical, then the superposition of its contents shouldn't cause a superposition of the gravitational field. A superposition might involve different distributions of mass, which normally would mean different spacetime curvatures. Perhaps a superposition
Space-time doesn't curve.
spacetimes. But if gravity is classical, then there's only one spacetime regardless of its content.
Okay, listen to me. Here's the thing about space-time. It doesn't curve. Yeah, no. Because I have disproven time dilation, because the clocks simply have the light lag behind them, that means time dilation, the effect noted as the difference of how time works when you're away from the gravitational force slightly from the Earth, as in being not in close proximity to a planet or a star or whatever, gives off gravity, like a black hole. The galaxies, quasars, pulsars, whatever you want. Because there's no difference in how time works, that means there's no difference in how space-time actually exists with the curving function and whatever. If you want to think about space-time curving, you might as well call a magnet that pulls an object. If you move at a certain speed, it will only pull at a certain amount, and that's called space-time curvature on a microscopic scale. If you want to call it that. But it's not. It's just a magnetic attraction. Boost that up into a planet where you have all the different masses of the planet exerting a force that is also slightly gravitational and such. You end up, why is it in white mode? I don't know. I'm not, shush.
This could lead to a tension between the gravitational field and the matter producing that field. The Diosi-Penrose approach says that when the tension gets too large, the wave function collapses. Another way to think about it is that the fuzziness in the matter distribution is within a certain range of matching a single spacetime curvature, and in that case it can stay in superposition. But if that distribution of matter strays outside that range, then its superposition collapses into a well-defined matter distribution. Oppenheim's post-quantum gravity is slightly different. It states that the gravitational field contains random fluctuations called gravitational diffusion that mess up quantum superpositions, causing them to collapse.
You have to realize we are feeling the gravitational effects of two black holes collapsing into one black hole. We felt that from here because of gravitational waviness. Okay, that means that there is, in fact, a basic field, has nothing to do with mass, has nothing to do with anything, it's just everywhere. Your gravity of literally everything just had a big bump, as if you just pushed a piece of the sheet around on your bed and you decided to tug on it a little bit, and we felt it across the other side of the bed. That's what happened with the gravitational stuff of the black holes. They did that when they collapsed together. That happened. Meaning, even stuff not in our own galaxy is felt by stuff here. It's amazing that, stuff in our galaxy could affect us. That's fine. But this is stuff outside of our galaxy. Also, can make a ripple that ends up affecting us. because all of space is occupied simultaneously by the same field. You have to come to grips with this.
Oppenheim and the Diossi and Penrose approaches make a similar prediction that there should be a stochastic quality to the gravitational force or its effect. This gravitational diffusion might be the most straightforward thing to test, if it exists. It would imply that
What is what is that word he used? Stochastic?
is a fundamental limit to the precision with which any mass can be measured. So if we can build a set of scales with a certain very high precision, then if the weights it measures appear to fluctuate outside that precision, it may suggest an intrinsic uncertainty in the gravitational field. The most accurate experiment measuring an object's mass conducted.
We already have experiments talking about gravitational fields. It's a freaking set of lasers. And they go wobble wobble. They're very sensitive and they're extremely large array of fields. Like they have these lasers. It's literally like, I think the laser goes in one direction an extremely long distance and an extremely other direction the other distance. And that gives you only a small area of where you can feel these effects, and that's how we know about that whole merger of the two black holes stuff. But you have to realize there's gravitational wobbles coming from every point in the universe. Eventually they just become sort of noise. Except for the key points that happen that are more highlighted.
So far has led researchers to rule out versions of the theory with rapid space-time diffusion.
He said he felt a disturbance in the force. We literally felt something. Galaxies, never mind.
Implying that any gravity-induced collapse from this mechanism is very weak. Oppenheim and team propose other tabletop experiments that could constrain this better in the future, rather than look for the funky behavior of the gravitation.
Did you know that we had a gravitational setup that was supposed to check on gravity, and we had to cancel out all the other noise, which included the cars and the people and the stuff in the town nearby? We knew about all those different signatures and could track that. And if we had a simulation doing it correctly, using this one gravitational sensor, we could know everything that is in the area. We would know that it is a certain proximity from everything, or we would even be able to know, like, almost exactly where everything is. It's crazy.
Field, we can also approach this from the other side by trying to see when the collapse of the wave function happens. If we can see where quantum superposition gives way to classical matter, we may be able to figure out whether it's gravity causing that collapse.
Fascinating concept. What if, how if you take a pair of quarks and you rip them apart with an incredible amount of force, but if you do it, the individual quarks will result in two new pairs, each one of them making a brand new buddy for itself. So you start with 2, you end up with 4. That's because they're pulling other bits out of the everything else that is otherwise just energy everywhere. Meaning, the stuff you need to make matter is in, like, literally the background radiation of the universe. Just pull it out.
Both the Oppenheim and Diossi-Penrose models, as well as any of the family of models known as objective collapse theories, predict that wave function collapse becomes increasingly likely as the object grows in size or mass. If any of these ideas are correct, then there should be a limit to how large an object we can put into superposition for any appreciable amount of time. So far, we've not found such a hard limit, and we've been able to put some pretty big things in superposition. For example, getting interference patterns from large molecules
What? That's the
in the double-slit experiment.
That's not large molecules, that's a single electron. Having, again, the electron is a particle, it's a tiny dot, it is a bar magnet. It has an electromagnetic field aura around it, which is why it connects to the atomic nucleus in the first place. It's why it doesn't just zip off, because it's not a neutron or a neutrino. It connects to nearby matter, and that nearby matter of the double slit is, guess what, small enough and close enough that any tiny deviation with your electron gun is going to make it so that you will shoot the electron near the slits in the wall that is making that is the thing that the beginning of the interference pattern. This pattern is waves in the electromagnetic field. The dot shows up as a dot because it's like poo sticks. It's a stick and there are waves, and the stick goes in one direction because of the waves. It has always been it has always been a stick. It has always been a particle. It never was wave function. Never mind.
Based on the largest systems that have been put into superposition, we can rule out theories where gravity-induced collapse is very strong. So we have some constraints on these ideas where a classical-ish gravity is influencing the quantum wave function of matter. And more advanced tests are being planned that may turn up something. Of course, it may be that gravity really isn't classical in the way that these theories propose. It may be that gravity really is quite quantum, just like matter. If that's the case, then we need different experiments. Two of the
I mean, do you even run a goddamn centrifuge? A basic centrifuge? I mean, all the stuff ends up pulling towards the edges of the thing, depending on how it's set up. Everything pulls towards the outer edge. Heavier stuff at the bottom, lighter stuff on the top, because that's how that works. Buoyancy and all that.
Properties of quantum objects are superposition, which we just talked a lot about, and entanglement. Quantum entanglement is when you have two quantum systems that each may be in a superposition of states, but
we were never able to prove quantum entanglement. We were only able to prove quantum, what do you call it? We divided a photon with a calcium atom so that it would be split in half, and each half has there's a form they take. And if you were to 180 that form, it actually looks exactly like the other half of the form. It's more like you created or stimulated for two separate light sources to be made out of the stimulation from the single light photon. Each one of them has their own curl, right-handedness and left-handedness, which is only like that if you only look at them head-on, as in down each of their respective barrels. You would notice they're more the same, or they're more of, like, imagine if you had a curlicue and you cut that curlicue in half like a noodle, you know, They're both the same curlicue going in opposite directions. They have the same shape still. But they do different things as they go in opposite directions.
Systems are also correlated so that the state of one depends on the state of the other. For example, a quantum coin could be in a superposition of both heads and tails, and a pair of quantum coins could be both in superposition but also be entangled, so they would be, for example, in the opposite state to each other. Even though each of the coins is fundamentally undefined in its state, if the first coin is measured so that its wave function collapses to either heads or tails, its entangled partner's wave function will immediately collapse to the opposite.
I think you don't know the definition of superposition. Superposition is a single object. It is a single, maybe combined object, but they're not. You don't call it entangled. You call it a singular object, or two objects occupying the same space. Is just, you can't use this diagram of two separate objects. They aren't two separate objects. Superposition means it's the same object. Quantum entanglement means that never mind.
Quantum entanglement sounds like an exotic phenomenon, but it's not. Quantum particles are constantly getting entangled with each other. In fact, every interaction...
You state that as if it's a fact, and it hasn't been proven.
...between particles generates entanglement.
Fuck the Nobel Prize. That was not good science, what they did. It wasn't.
Even if that entanglement doesn't last very long. We've observed these entanglements when the interaction happens via quantum forces, for example, when particles interact by exchanging the photons of the electromagnetic force. So what if we could cause particles to become entangled by a gravitational interaction? As I'll try to convince you, this would mean that the gravitational field itself has to be part of the entanglement of those objects, and space-time has to be in a superposition of states, which would mean...
Besides the fact that quantum entanglement doesn't exist, gravity would be affecting both particles anyway, separately, independently, local to their nearby greatest sources of gravitational flux, whatever object happens to be heaviest at the time nearby. Because they are not directly in the same area versus, like, they're not in the same range versus all objects, they would experience different gravities.
...in that space-time...
different tugs.
...has to be quantum. One particular proposal for this type of experiment was recently put forward. It's known as quantum gravity-induced entanglement of masses, QGEM. I'll describe the original version proposed by Sugatu Bose and collaborators in 2017. It uses a...
You literally are using magnets.
Stern-Gerlach interferometer. This is the device that first demonstrated the existence of quantum spin back in the 20s. The original version...
This is a quantum spin, or the part of the thing that is a magnet. It will then align itself either up or down because of the way that these magnets are formed. The magnetic field is flowing in a certain direction, and this device specifically makes it so that it will be either, well, it'll be affected in one way or the other, apparently, depending on how the particle itself is working.
Used silver atoms, which have a single unpaired electron in their outer shell. So this is the device that first demonstrated the existence of quantum spin back in the 20s. The original version used silver atoms, which have a single unpaired electron in their outer shell. So the atom takes on the quantum spin of that lone electron. That gives the atom a tiny dipole magnetic field. This causes the atom to be deflected when it passes through the external magnetic field of the Stern-Gerlach device. It's deflected upwards if its spin axis is pointed up, and downwards if its spin is down. Because
I can't help but be annoyed about the fact that if the first of all, it will polarize so that it only goes either up or down. It doesn't go like left or right changes, because this is a very directed electromagnetic field that they've made because of the way the device is shaped and how electromagnetic fields flow between the positive and the negative electromagnet, or stationary magnet that happens to have one of them is the one and the other is the other. It flows. So the thing is, ironically, it still is fluctuating as it moves through this, and the majority of it works with that electromagnetic field to move either up or down, depending on how it was when it got in. It could be that it is just more likely to curl its direction. And notice, this is an angle here.
quantum spin is quantum, all atoms will be measured to have either spin fully up or spin fully down.
Once it's out of that device, apparently the trajectory is straight, meaning the total length of the device can have a veering effect that is only either one or the other. It either goes up or down, depending on how the electromagnetic stuff of the actual silver atom, and that's what they're saying, is doing. So
deflected all the way up or deflected all the way down. There are no in-betweens for quantum properties like this. If the atom starts in a superposition state of being both spin up and spin down, then it'll end up in a superposition state of being physically up or down just before it hits the detector screen. So we've turned a spin superposition into a spatial superposition.
It has a chance of going in an upwards trajectory or a downwards trajectory. Nothing else fancy about that. Superposition, forget about it. There only exists the one path, and if you actually knew the form of the actual characteristics of the silver atom, you would know what it would do as it goes through the device. Just saying.
The screen, the superposition collapses into one or the other location. But we can also remove the screen and use more magnets to bring the spatial superpositions back together, in which case we turn the spatial superposition back into a spin superposition. Now if we measure that spin, we should find that it collapsed.
This is ridiculous for one very important reason. The particle went up, and then for some reason, instead of veering off in a trajectory that is on an angle, why would it ever do that? It is now moving straight forward. This means that something else is guiding it from one to the other, possibly. But why would it change trajectory so dramatically? You're doing something with it, clearly.
Just completely randomly into 50-50 spin up or spin down. Now, if we were to run a second Stern-Gerlach interferometer next to the first, the spins we measured at the end of the second device would have no relationship to the spins measured at the end of the first. Atoms in the different devices are uncorrelated because they're not
entangled.
But
I've heard this before because I've watched it before.
Now, let's move the devices really, really close together. The spin-up path of interferometer 1 is right alongside the spin-down path of interferometer 2. Let's pretend for a moment that the silver atoms can interact gravitationally. The spin-up 1 and spin-down 2 atoms tug on each other, ever so slightly, while the other paths are too far for the atoms to interact. Remember that the spin measurements at the output of the
You know magnets are more powerful than gravity, right? They don't fully override gravity, depending on how strong they are.
Interferometer 1 versus interferometer 2 used to be random, uncorrelated. Up, up, down, down, up should all be equally likely results of measuring those final spins. Any quantum interaction, though, should generate entanglement between these. So now, if gravity is quantum, the outputs of the two interferometers will be entangled and will be correlated.
Could you think of literally any other reason why these particles going through at the same time would have a spin up or spin down correlation? More likely than not. Is there any way that maybe the two fields which are close to each other end up making, and by the way, the interaction of the field versus the particle ends up making a best desired direction, which most likely is going to be opposites, and that's mostly because of how the electromagnetic field flows. So generally, they could end up binding in ways that make these flows that are symmetrical, and it has nothing to do with entanglement. They just happen to flow through the electromagnetic field at the same time and have the electromagnetic field forces them into that shape. There's no entanglement, just the same as if you were to take a single jet stream and shoot it between two balls, they'll spin in opposite directions. Oh wow, that's not even like hard to conceptualize. You can just do that.
For example, depending on how this is set up, you might find that the interferometers produce opposite spin results to each other very, very slightly more often than the same spin results. Now,
okay, the thing about the difference between the... Okay, so if you really want to think about it the other way, instead of thinking about a jet stream going between two balls, think of the balls going against a substance. So the first ball, it's like a couple of cogs. They want to mesh together. As they roll forward, they want to possibly roll in a way that correlates with the other one, because the way that they flow electromagnetic field, like I said, is guided by each other. Two of them will want to flow clockwise, counterclockwise, or counterclockwise and clockwise. In other words, one going inward from, let's say, west, north, east, and the other one going inward from east, north, west. If you can think of that as the rotations, you know, clockwise, counterclockwise. And the same could happen with it going in the opposite direction, and that's how they end up correlating, but it's not entanglement, it's correlation. You should know better.
Single atoms are way too light to produce a measurable entanglement. But what if we could do this with many, many atoms? Specifically with a nanodiamond. These are tiny diamonds with widths measured in nanometers. A little defect inside the diamond crystal structure can be created by removing one carbon atom and replacing it with a neighboring nitrogen atom. This leaves an unpaired electron, which gives the nanodiamond a net spin. The same technology.
Basically, it is a larger version of the silver atom. Only this is a molecule instead of an atom.
Is actually a candidate for qubit storage in quantum computers.
No.
So we create nanodiamonds and put their unpaired electrons in a spin superposition, then shoot them through the pair of Stern-Gerlach devices.
Right.
In principle, we should get a spatial superposition of these relative...
Oh, right, I forgot. This guy doesn't know that electromagnetic fields are basically like a liquid. It's the same thing. The electrons or the silver ions, these are, or the diamond thing, these are the pebbles. They're affected by the fields the same way objects being shot through water would basically work based on the fundamentals of how that is. You can do a couple of these experiments yourself. Just have a couple of beads of something in water and make sure they can float or whatever, and just like you know how exactly that will work. Easily done.
Massive crystals. And if gravity is quantum, we should get entanglement between the devices that will be reflected in correlations in their final spins.
Correlation.
What would all of this mean if it proved to work? Well, from the point of view of particle physics, the masses get entangled when gravitons are exchanged between the two masses. This is just like in electromagnetism, where photon exchange leads to the electromagnetic force and sometimes to entanglement.
I still don't believe that photons are small enough to be the carrier of electromagnetic field. It very much still could be, but hear me out. Photons are affected by the electromagnetic field. They are not just an agitation in it.
We've made a video before on how hard it is to detect single gravitons, even in principle. So this entanglement between the two masses in the QGEM experiment might be considered indirect evidence for the existence of gravitons, the hypothetical quantum carrier of gravity. From the point of view of general relativity, the superposition of gravitational forces could be interpreted as a superposition of space-time geometries. So space-time itself would be exhibiting one of the most quantum of all properties. In general, a positive QGEM result would be strong evidence that gravity is indeed quantum. These are just some of the experiments that have been...
If you don't misunderstand what's happening, but you clearly are, because you don't know how electrons or any little bar magnets, any of those things, objects affected by electromagnetic field, you're literally using an electromagnetic field in an experiment. If you don't understand how that works, you're going to come up with false positives about all sorts of stuff. It doesn't prove anything. You've just used up a bunch of your brain power thinking it is, but it really could be completely different, and reality is, it's different. Unfortunately. You just aren't trying to grasp it. Sorry.
Or in some cases actually conducted to test some of these ideas about the link between quantum mechanics and gravity. Whether to find quantum effect in the gravitational field or to show that gravity doesn't even need to be truly quantum. There are lots of other ideas and efforts in progress beyond these, and there's a good chance that some will bear fruit, perhaps finally unlocking that century-old mystery of the quantum nature of space-time.
I don't want to hear the rest. I think it's just...
Thank you to Brilliant for...
Yeah. Okay, so the thing about this is it's a lot of bunk. It is a lot of the goddamn... I don't like hearing about the double slit experiment. No one gets it right. No one gets... we have seen other experiments that are recent, or even years ago, where we know how electrons are tiny bar magnets. And when you do experiments with bar magnets and how they change the electromagnetic field and how you can visualize the electromagnetic field using this special disk that they had, it was fascinating. You can see the flux field of the electromagnetic stuff. It changes how this disk interacts, so you can visualize exactly what's happening. It's like this crescent of friggin', or no, what's the word? It's a donut shape, torus, that is around the particles, the electrons, literal, and like most atoms. If you understand the actual forces involved, none of this is a goddamn mystery. If you keep on being like these people, this is not just one person. I'm not gonna focus any attention on just him. This is PBS. It's a company. Okay. It could be a company of scientists like Bill Nye and everyone else. And they could all be thinking that they're aware, like NASA, thinking that time dilation is a real thing and it's not. Is the echo chamber and everything, you keep on thinking in these terms of like, oh, the electron behaved like a wave, so maybe it was actually a wave at some point, but then when it hits the thing, it turns into a dot. It was always a goddamn dot. It was never a wave. The wave is a separate function. I give off heat. I never was heat. I give off heat. An electron flows the electromagnetic field. It's a pump. That's how bar magnets work. They pump electromagnetic field. They excite it. And when you have something like a generator, you're moving those electromagnets, those little bar magnets. You're forcing the electromagnetic field to be reacted on, and it causes things to fluctuate in the wires, doing the AC thing, doing the DC thing, and you end up with power. That's how everything is fundamentally powered. You excite the stuff, and it ends up wherever, doing whatever. This, however, the one thing I will say that is anywhere near nice about this video, the idea of an extremely sensitive scale. And guess what? They have built extremely tiny needles, the size of a single atom, but it is a tiny pinprick. And if anything's going to be the most sensitive thing in the world, it's that. Why don't you know about this stuff? Research a little. Understand that we already have these things, as well as we have gravity sensing things you've done videos on. You've done videos on the gravitational observatory. You have done videos talking about this whole thing. Frickety frickety frick. Oh, dude, this is my favorite frickin' thing in the world. The cosmic frickin' lightning that we are in. Although it's not lightning. Apparently, the entire area of the universe, our galaxy is a tiny little dot on that entire thing. This thing, this
500 million light years.
Those are all galaxies. Every pixel in this is a galaxy, all flowing towards this great attractor thing. And guess why that is? It's a goddamn soup. We are in an electromagnetic soup, and it all flows similarly to how if you were to pull on a sheet. If something is pulling, if something had the ability to shoot forward with enough tug, the flow stays, and that flow continues to pull things in that direction, as long as there are other objects that are also able to move and pull things, and the more it happens, the more things get stronger and pull things in. This is the freaking...
All moving under...
This is where we are. We are on one of those hairs. Our galaxy is a tiny pixel on one of those hairs, all being pulled towards this middle part. This middle part. That's crazy. If you can't concept the fact that gravity is affecting things because the field of everything is all joined together and it's all able to flow in these directions that are so goddamn beautiful. It's a real thing.
A vast mutual gravitational influence.
It's not just one vast gravitational influence. Literally, this is like the finger, it's not the fingerprint. It's like the flows of a river, where everything starts from the outside, but instead of a river, what it really is, you know how if you plug in multiple things to an outlet, the more power gets pulled from the outlet? If you can overload that thing, well, all of those separate objects are like single strands of tug. And because of the wires, they're directly connected. Now imagine that kind of flow stuff is happening, but on a galactic scale, on an intergalactic scale. And you are here. This freaking is amazing. That's real stuff. That is something that actually is. Where is the goddamn thing about the I'm sure they talk probably even multiple times about the gravity sensing. I just want a picture of the damn thing. Or if I were to pay attention or like properly look it up, I could show you a picture of this thing. It's just basically two lasers, and the difference of how the lasers are with a tiny little bit of difference is how we can check and know gravity waves in the first place. It's like we noticed a ripple from black holes merging. Oh my god, there's so much crap here. I call this crap. Sheesh. It just keeps going, doesn't it? Like, my god. Have you not learned a damn thing in your 5 years of doing this? I'm being real with you right now. Learn how the electromagnetic field actually flows like a goddamn liquid. Learn how electrons are particles in that liquid. And everything else is all just moving around based on what's happening with the liquid, and the stuff is also moving the liquid. That's why, like, if you look at a freaking galaxy, gravitational wave background discovered. Freaking meant to be.
It was pretty impressive when we built.
Yeah, you built this thing. It has lasers, and it shows us that there was this big merger out in space. It was awesome, really cool, and where the is it that? No, that's Arecibo. I know that satellite. It was great. It was a good satellite. It was a fun satellite. I don't know where the picture of the thing is. Is it that circle? No, that's something else entirely. Or is it? I don't know.
Waves that rocked the rowboat in the ocean. A session span masses of millions to billions of suns. Space would produce expected would be with balls into black holes.
Uh-huh. Pay attention, trust me. Anyway, so we already did experiments learning about how some of these things work and all of that. Listen, I haven't been
Itself is one of
look, I haven't been only working on electromagnetic fields and gravity, which, let's face it, I admit, I haven't fully explained how gravity works. Except for its momentum, except for you still have the electromagnetic soup that we're all in. It's still just there. Like, you think that electromagnetism is small, and then you realize it's a goddamn sunspot. It's as big as a freaking sunspot. And the electromagnetic field around the planet. How do you call that small? And then you got all the energy that's flowing out into and throughout the solar system and throughout all of outer space. And you realize it's freaking everywhere. It's like our own backyard is only as clear because the sun literally pushes everything else that is able to be, like, unless it's around a planet, the sun is pushing out all the other stuff. So you end up with the belts and everything else. It all sucks in towards nearby gravitational stuff. But other than that, the local area is pretty damn blown away by solar winds constantly. No joke. No exaggeration. Radiation pressure enough to push everything else out. And we're moving through the galaxy, and it's literally plasma all over us. But we still see, like, everything else out there. It's just fascinating how that works. Look, because time dilation doesn't exist, I've already proven that in other videos multiple times. Although, I have to admit, there was a thing I tried telling people about how you can know your speed without reference to literally anything. You don't need to be looking at something nearby. You don't need to know anything that's happening outside of your... Let's say you're in a box and you only had this item, you could still know your speed. It's a flashlight. As long as you're not going faster than the speed of light, this flashlight, any flashlight, will give a cone that is of a certain angle. And if you know how the flashlight's designed, you know once at a certain distance, the circle of light will be a certain size. You can do this all at home. Everyone can do this. You could just have your flashlight turn on, and it'll only illuminate a certain size area. And the further away you go, the bigger that circle goes. And also the thinner it is, and more diluted and less bright, obviously. So, knowing the dynamics of that, you can know your speed and your telemetry if you're like going on a circular orbit or something without looking outside whatsoever, with no concept of time, except for the fact that light is constant and how its speed works. Simply can calculate your speed as an object. So, with this basic sensor, you can know the speed of your satellites, you can calculate how fast they're going very precisely, and then keep track of that, know how your speed is affecting the clock and the light traveling inside of the clock, as well as how it's traveling through space, how you're traveling through space based on the angle you're going. You can figure out exactly how fast you're going, but you can also figure out how to set your clocks correctly, because you know your speed perfectly without using a clock. Then you can use that speed to set the understanding of you're traveling at this rate, the light will reflect at this angle. That same light could even be used in the clock, and you'd have to shine it on every time you do this. You cannot shine the light up and down. You have to shine it forward at an angle so that the reflections are good and things. There you have it. You have a clock that's calibrated to work correctly, and there won't be any time dilation issues because you'll be compensating for how light works in this scenario of the target's now over there. It's not time dilation. The target is over there instead of here. That's all that's happening. Once you have that, then you know, and knowing that there's no such thing as time dilation, you know there's no such thing as the curvature of space-time, so that different areas of time have different areas of space have different rates of time, any of that nonsense. You can observe the universe as it actually is. The world would be a lot better off for it, because you end up with people thinking, oh, you go near a black hole, you're going to end up with your feet going at a different rate than your head. That doesn't happen. Time is the same everywhere. It's only how light is perceived that is different. Perception is not the actions of stuff. There is a grand difference. And the one scientist that I disproved recently, he got it almost right, and then flipped around, still said time dilation is the thing. He failed the course. And he's getting higher grades than everyone. He's getting views all over the place. Other people are talking about it. They're all getting the views. The difference is, I don't make a great presentation about it at all. I don't make any presentation about it. I don't even try. I say things like east, north, west, or north, east, south for how it will rotate, instead of thinking about like how to properly say it, how to properly show it. Because theater of the mind can only go so much. If you have a diagram in front of you, it makes it a lot easier to understand that stuff. If you're using theater of the mind, you're using your head. You're not using stuff that is, like, it's no different than having a diagram in front of your face. But you're actively thinking about how it should be working. It's the way I think about it. But there's literally no difference. If I actually make a proper presentation, yeah, more people who have lack of theater of the mind would be able to follow along a lot easier. But I'm not talking to majoritively benefit you guys, although who are everyone. I'm here to talk to the scientists who are working in all this stuff. I'm here to talk to NASA. I'm here to talk to PBS Spacetime, Kyle Hill, and every other person talking about being a science communicator. Please get your shit together and get it right. Stop romanticizing science and get it done correctly. Do the actual scientific method. Kyle said, oh, well, if the speed of light is constant, then the only thing that could be different is the time. But at the speed, distance, and time are the three factors, you're not even considering that distance is the factor, which it is. Literally, you go faster, then you are forcing light to also move at a further distance per second. How do you not see how that's a greater distance? And of course, that makes it so light will lag behind, causing a difference in the tick of the clock. It's not time dilation. It isn't. Please grow up. Like, so many people, they talk about the double slit experiment as if they actually know what's going on. But they don't even think about electromagnetism as a fluid. And I'm like, you cannot state things as facts without knowing the facts. Well, it doesn't stop them from doing it anyway. Thankfully, I've noticed if Kyle Hill were to be rated on a scale of his grades, this is simply one mark negative out of the thousands of marks that he's got positive. Tiny little blemish. But it spreads. It goes from there's time dilation to there's ways that you talk about black holes, there's ways that you talk about how gravity works, how light is twisting with matter, and time is twisting with matter and things, and the matter is twisting how time works. Romanticism. It's disturbing. I want to give a lecture in I want not a lecture, but I want to give like a basic experiment. I want to teach, but I don't want to teach just random people. I want to teach the people who've been working on this for so long, because when I first learned about Stirling engines, for example, that pissed me off too, because everyone I listened to who talked about Stirling engines didn't say how they actually worked. It's not that the top of the chamber and the bottom of the chamber are different temperatures. The inside of the chamber is a different temperature compared to the outside. Now, for people who don't understand what I'm talking about, it flies over their heads, they don't care. But if you do understand what I'm talking about, the only reason the top part would be wanting to be cold and the bottom part would be wanting to be hot is because you want to have the inlet and the air going in be as cold as you can, so that when it goes into the chamber, the heat forcing it to expand will force it to expand more than standard room temperature. If you have it colder, instead of being as big as it is in room temperature, the colder state is actually more compressed. You can have a Stirling engine work in reverse, where it goes from hot to cold, doing the exact same thing. Instead of being hot, now it turns into being cold, and the pressure that it gained from all that heat is now compression instead of expansion, and everything keeps flowing in because it keeps compressing, leaving more room for more hot air to flow in. If you leave a circle between the two of them, you have constant flow of hot and cold. Then you just have to keep on applying the energy that makes it hot and the radiator that makes it cold. It's almost that simple. And then you can have a system, again, this works in space. You can take the cold from outer space I know what you're thinking. But you can take the cold from the outer space, use the heat from the inner ship, make a Stirling engine, combine it, and you have power without having to put any fuel on the thing whatsoever. It's just a difference of temperature. Your operating systems of the goddamn router that I have a fan on my router so that it doesn't overheat. It's fucking stupid. It has a fan. Instead of a fan, transfer that heat into a Stirling engine and suddenly you just have power. How much? Who cares? It's excess power. It's better efficiency. Use hot air balloons and zeppelins for a space elevator. Goodbye. Please consider